Okay, so as you can tell, I'm back in my office, and it is now a day after I made the video before this one, so I'm not completely sure where I left off, but I do know that we are talking about this interesting situation here, where we have intersecting characteristics, and now we have to figure out what's going on. And what we decided was that our solution must have some discontinuity, like rho is a function of x and t. And so if there's intersecting characteristics, it must mean one of our underlying assumptions was wrong, in particular that rho is continuous. So we're going to assume that there's this curve of discontinuity that rho has in the xt plane, and now we want to try to determine an equation for that continuity, or an equation for that discontinuity, and our solution will be of the following form: rho of xt is going to be equal to 2 to the left of the discontinuity, and it's going to be equal to 1 to the right of the discontinuity. But I actually need to get an expression for the discontinuity in terms of x and t. Like, what is the equation for that orange curve there? And so that's what we're going to work on now. And I'm actually going to change. I'm somewhat apologetic for this, but not so much. I want to change the notation for this. So I'm going to write this as partial t rho plus partial x q of rho, only because I was using q above equals 0. And again, remember, when we have an equation written in this form, we say it's in conservative form. And to do the analysis that we're about to do, we have to have it in conservative form. Okay, and I'll explain how that relates to the previous equation in just a moment, but I'm going to sort of, given an equation written in this form, and I'm going to try to determine how we can find a general expression for the shock location. So the shock location is going to be called xs of t. So x is equal to xs of t. So this is going to be the shock location there. The subscript s doesn't have anything to do with the s in the method of characteristics. It just means s for shock wave. Okay, and so what I'm going to do, I'm going to look over this little rectangle going from A to B, and I'm going to fix a t value, and I'm going to integrate something. I'm going to integrate the density from A to B. And our assumption is that even across a discontinuity, rho is still conserved. So in other words, d dt of this is going to be equal to q of bt minus q of at. Again, this is just conservation. This is just the conservation law that we derived several videos ago, but I'm just applying it across, this discontinuity here. Now, since I'm integrating across a discontinuity, I really need to separate this like an improper integral from A to the discontinuity, then from the discontinuity to B. So the discontinuity is going to go from A to xs of t rho of xt dx plus the integral from xs of t to b rho of xt dx. And so again, what if I look back up in the diagram here, I don't know what the orange curve is, but I know it has the formula xs of t. And if I fix a particular t value here, then I'm integrating from I'm integrating from this point to this point, which is xs of t, and then I'm integrating from xs of t to b, just for this fixed value of t. It's a fixed but generic value of t. Okay, so now what I want to do, so this is going to get a little bit messy, but what I want to do is I want to pass the derivative, the differentiation, into the integral. But it's not so simple, because on each one of these integrals, I have a function of t in the limit. And so to use this, we have to use the Leibniz rule. If you forget what this is, do what I did and look it up on Wikipedia. I mean, not because I forget what it is, but because I always forget what the formula is. Okay, and I guess I'm too lazy to think about it myself. But this integral on the left-hand side now becomes the following. It's the integral from a to xs of t times the t derivative of rho. And I'm not going to write all of the x and t arguments because there's going to be a lot. Plus the t derivative, xs of t, times rho. And I'm going to introduce some u notation here and talk about it in just a second. S minus t plus the integral from xs of t to b, the t derivative of rho, and then minus the t derivative of the shock times rho of s plus comma t. Okay, so what is this s minus and s plus? This is just rho s minus is the limit of rho coming from the left-hand side, and rho of that's rho of s minus, and rho of s plus is rho, the limit as rho approaches from the right-hand side. So if I want to be very precise about this, rho of xs minus comma t is going to be equal to the limit as x approaches xs of t from the left-hand side of rho of xt, or another way to write this would be the limit as epsilon goes to 0, rho of xs of t minus epsilon comma t. Either one of those would work. And then there's going to be a similar definition for rho xs plus. This is equal to the limit, I'll write it in the second form, epsilon goes to 0, rho xs of t plus epsilon comma t. So the s minus is the limit from the left-hand side to the discontinuity. The s plus is the limit from the right-hand side to the discontinuity. Okay, so now if I'm looking to the left-hand side of the shock or to the right-hand side of the shock, so either for the a to xs or xs to b, in both of those regions, rho satisfies the PDE. So now I know that the integral from a to xs of t partial t rho, well, this is equal to the integral from a to xs of t minus the x derivative of q xt dx. And then this, again, xs of t, we're going to the shock, so this is going to be equal to, by the fundamental theorem of calculus, this is going to be equal to q of at minus q of xs minus t. Okay, and similarly, if I look at the integral from xs of t to b times the t derivative of rho, this is going to be the integral from xs of t to b minus the x derivative of q. And then this is going to be equal to q of xs plus t minus q of bt. Okay, so copy these expressions down because I'm about to erase them and replace these integrals with them above, in the above. Okay. Okay, so now I have just rewritten this expression with my computing the integral of rho in terms of the flux q. And we already have seen that this whole integral here is equal to q of bt minus q of at. So this is equal, q of at minus q of bt. So there's a typo here, sorry. Q of at minus q of bt. Okay, and this is equal to q of at minus q of bt. Okay, so now what happens if we solve this equation for x dot? Oops. When we solve this equation for x dot, we get that x dot s of t is equal to q of xs plus minus q of xs minus divided by rho of xs plus minus rho of xs minus. Okay, so in other words, this is the jump in q across the discontinuity over the jump in rho. So this, the notation is this q box over rho box. Okay, and so if we know like maybe what xs of 0, if we know xs of 0 is equal to x naught, then we can compute, then we can use this to compute what xs of t is. This is now going to be a differential equation involving xs. So how do we apply this idea to the example that we're working on? Well, I'm going to have to insert a new page to do that. If we go back to the problem that we have this problem here, though remember we modified it. Somehow my document lost these annotations. We modified it so that that 2 was equal to a 1. Okay, so once again my computer has done that adorable thing where it just doesn't work anymore, where the pin stops working. So this is the PDE that we have. And so let me come back down here and try to figure out what the solution is going to be. And in other words, I need to figure out a good expression for this, this discontinuity. How can I write this discontinuity in terms of x's and t's? Okay, well, I made an embarrassing error in this video. That's why I removed it and then re-uploaded it. Thank you to Kyle for pointing that out. When I write this in conservative form, it's rho t, partial t rho plus partial x rho squared over 2. The rho squared over 2, or sorry, the rho should be the derivative of the rho squared over 2, and that's equal to 0. And so this tells me that q of rho is equal to rho squared over 2. Okay, now if I come back up here, I know to the left of the shock it's equal to 2, and to the right of the shock it's equal to 1. So this tells me that x dot, well, remember it's the jump in the jump in q over the jump in rho. Okay, so the jump in q is rho squared, so to the right, rho is equal to 1. So this is going to be 1 squared over 2. To the left, it's 2 minus 2 squared over 2. And in rho, it's going to be 1 minus 2, so this is 1 minus 2. So this is going to be 1 half, 1 half minus 2 over minus 1, or 3 halves. And so this is equal to 3 halves. This is the shock location, I should say. Okay, well, I know the characteristics first intersect at time t is equal to 0. Where are we? They first intersect at time t is equal to 0 here. Again, to the left 2, to the right 1. They intersect there when t is equal to 0. And I know that x of 0 is equal to 0. So this tells me that xs, for the shock, xs of the shock is equal to 0 because it happens when time is equal to 0 and there x is equal to 0. So xs of t then is going to be 3 halves t. All right, so let's come back up here and fix what I have. So I look up here. What I want to do that I think I didn't do in the video is I want to actually sketch the location of the shock wave. So the shock wave, I'll do that in purple. Xs of t is equal to 3 halves t, or thinking about this like as the vertical variable being a function of the horizontal variable, this is t is equal to 2/3 x. So I'm going to go over 3 and up 2. This is going to be the location of the shock. Now what I want to do is I want to redraw all of these characteristics. They're going to be flowing into the shock. Okay, so the blue characteristics from the right, these are going to have slopes of 1/2. And so they're going to be something like this. They're entering that way. And the characteristics from the right, they're going to have slope 1. So they're going to be entering this way. Like this. So these red lines are parallel. And I know rho is 2 to the left-hand side, and rho is equal to 1 to the right-hand side. So then I can write my final solution as u of xt is going to be 2 to the left of the shock, 1 to the right of the shock. The equation for the line is t is equal to 2/3 x. So this is going to be when x is less than 3/2 t, and this is going to be when x is greater than 3/2 t. Okay, so that is that for this video. Sorry about my error.